In this lesson, we're going to look at definite integrals. We'll review the process that you would have already previously learnt in methods, called the fundamental theorem of calculus, and then we'll look at a process for definite integrals, including integration by substitution. Okay, so first off, looking at the fundamental theorem of calculus, it is simply that the integral between 2 points b and a of some function with respect to x will be the difference between the primitives of each of those points. So in other words, this is the primitive, that capital F, and we're subbing in those 2 points b and a. Really quick example with this is we're finding the integral between 2 and 0 of the function 3x squared plus 2x plus 4 with respect to x. Okay, so step 1 is we want to find the integral here. So this becomes 3x cubed on 3, 2x squared on 2, and 4x. You don't have to worry about adding c because we're going to subtract the function from itself, and adding c would be redundant. So, and it's between 2 and 0. If we can simplify this integral, it will make it easier as well. So we can cancel those 3's, and we've got x cubed. Cancel the 2's, and we've got x squared plus 4x between 2 and 0. Now the fundamental theorem of calculus says that we've now got the primitive, and we just need to sub in 2 and sub in 0 and find the difference between the 2 points. So we've got 2 cubed plus 2 squared and 4 times 2, and we're subtracting 0 cubed and 0 squared and 4 times 0. Obviously we know that that will be 0. We've got 8 plus 4, which is 12, plus 8 is 20. Take away 0, and we're left with 20. So the integral is simply 20 units squared, or square units. All right, so that's the fundamental theorem of calculus. It's pretty easy. I'll do one more example involving a exponential. Okay, so in our second example, we're looking at the integral between 1 and 0 of the sum of an exponential function and a linear function. So we have the integral first. The integral of e to the power of 3x will be 1/3 e to the power of 3x. And integral of x will be x squared on 2. And that will be between 1 and 0. Now we can't simplify this because they're both fractions in their simplest form. So we're going to sub straight in. So we'll sub in 1 first. We've got 1/3 e to the power of 3 times 1. And 1 squared on 2. And we'll subtract 1/3 e to the power of 3 times 0. And 0 squared on 2. So this gives us 1/3 e cubed plus a half, and we're subtracting 1/3 plus 0. All right, so now it's just a matter of simplifying. We've got 1/3 e to the power of 3 plus 1/2, take 1/3. We want to get them all over the same denominator, so this will be 2e cubed on 6. This will be 3 on 6. And this will be 2 on 6. So we end up with 2e cubed plus 1 all on 6 units squared. Okay, so again, you can see the process is pretty straightforward. As long as you can find the integral, and you can sub in b and a, and find the difference, and that will give you the definite integral. So now we're going to look at the process when we're looking at integration by substitution. Okay, so with integration by substitution, we're going one step further. We already know our process with integration by substitution, so we're going to follow the general process. But as we're going to change to du with respect to u, we need to convert the given limits to u values as well. Right, so this will be our approach. We'll look at an example because that's the easiest way to do this. And so if we look at the following example, when we focus on the integral, we'll notice that the integral is clearly an integral by substitution question. So let's just first consider, without the given boundaries, the integral of 3x square root of x squared plus 9 with respect to x. Now we should be able to see the derivative relationship between x squared plus 9 and 3x. So we should be able to say let u equal x squared plus 9. Now as we can do this, we can say du dx will be 2x, and therefore dx will be 1 on 2x du. And we can perform our substitution. We've got integral of 3x square root of u, and instead of dx, we can replace that with 1 on 2x du. Our x's cancel, which is very important to the process, and we end up with 3 on 2 integral u to the power of 1/2 dot du. Okay, so the rest of our process for finishing off this integral is pretty straightforward. 3 on 2 multiplied by u to the power of 3 on 2 and divide by 3 on 2 plus c. Now, we're dividing by that entire fraction, so it's going to cancel, and we just end up with u to the power of 3 on 2 plus c. We don't have to worry about utilizing plus c when we do our definite integral, but we'll go back up here, and so now we'll look at, now before we jump into the integration, we want to find u in terms of x for the limits given. So the lower limit is x is equal to 0, and the upper limit is x is equal to 4. Now, if we want to find u, we know that u is x squared plus 9, so we've got 0 squared plus 9, u will be 9 as our lower limit, and it will be 4 squared plus 9, so u will be equal to 16 plus 9, which is 25. So that changes our limits, and so we can say that the integral between 4 and 0, 3x square root of x squared plus 9 with respect to x is the same as the integral between 25 and 9. And when we simplify this down, it was 3 on 2 u to the power of 1/2 du. Alright, this is going to be much easier now. So this will be 3 on 2 u to the power of 3 on 2 over 3 on 2. And remember, they cancelled. And we're between 25 and 9. So we now have u to the power of 3 on 2 between 25 and 9. So this is square root of 25 cubed, take away square root of 9 cubed. So this is 5 cubed, subtract 3 cubed, 125, take away 27, which leaves us with 98 units squared. So hopefully that makes sense. You can do it the other way. You can sub x back in and use the values for x, but it does complicate things a little bit. This makes it a little bit smoother and easier. Okay, we'll get one last example. Okay, so in this final example, we're looking at the integral between pi and 2 and 0 of cos cubed x dx. Now, this one's a little bit of a tricky one. I'm going to say that we're still looking at the integral between pi and 2 and 0, but we're going to break up this cos cubed into cos x and then cos. squared x. And cos squared x, using that Pythagorean identity, we can say that cos squared x is equal to 1 take sine squared x. So we can say that this is the integral pi on 2 and 0 cos x and 1 take sine squared x. Now this is helpful because we can say, at this point, we can say that u is equal to sine x, because we can see that there's a derivative relationship between sine x and cos x there. So du dx will be cos x, and therefore dx will equal 1 on cos x du. Now at the same time, we can say the lower limit, x is equal to 0, and therefore u is equal to sine of 0, which will be 0, and the upper limit, x is equal to pi on 2, so u is equal to sine pi on 2, which is equal to 1. Keep in mind we're just subbing in to this here, u is equal to sine x, and so we can rewrite this problem, the integral between pi on 2 and 0 cos cubed x dot dx as the integral between 1 and 0 cos x and 1 take u squared. Dx is now 1 on cos x du, so we've got a cancellation there, and we're looking at the integral between 1 and 0 of 1 take u squared du. So the integral here is nice and easy. We've got u take u cubed on 3 between 1 and 0. And when we apply that fundamental theorem of calculus, we've got 1 take 1 cubed on 3 subtract 0 take 0 cubed on 3, which we know is 0. So we have 1 take 1/3 take 0, and we're left with 2/3 units squared. Okay, so that completes the lesson. This process of applying definite integrals is definitely something you want to practice to become fluent in. When we start applying this in the next integration topic, application of integrations, it will require you to be quite fluent and be able to do this as just part of your process when looking at more complex scenarios. All right, thank you for listening.